Hi there, my name is Dr. Matt Lukeman, and I'm going to be going through a tutorial with you to teach you how to name organic molecules. So to begin with, I think what we need to first talk about is the way we draw out organic molecules. Organic molecules, to begin with, are ones that contain carbon atoms, often connected to other carbon atoms as well. And typically other elements are there as well, like hydrogen, oxygen, and nitrogen. We'll be looking at lots of examples in the next coming up slides. One thing that makes organic molecules a bit of a jump from the molecules you normally deal with in first year is the fact that organic molecules often contain several central atoms. And even small organic molecules we would consider small, can have many atoms, many bonds, many lone pairs, and fairly complex Lewis structures. So I have a picture here of 2-propanol, which is also commonly known as isopropanol or rubbing alcohol. And this is a relatively small molecule. It only has 3 carbons and 1 oxygen and a bunch of hydrogens. And you can see from the structure here that it's a fairly complex looking molecule just from first sight. What we often do to simplify the way structures are drawn is in organic chemistry, we come up with simplified versions of Lewis structures. We kind of use them as a shorthand where we don't show all of the bonds, all of the lone pairs, or things like that you normally show for Lewis structures. We call these simplified structures either bond line or skeletal structures. And these are the rules that we use when we simplify the structures. First of all, we don't draw any lone pairs. We don't draw carbon atom symbols, so we won't be writing the letter C anywhere. For carbon-hydrogen bonds, the hydrogen symbols, so the H's, are not shown, and the bond lines between the carbon and the hydrogen are also not drawn. But when hydrogen is bonded to something else other than carbon, we do draw the symbol in, but not the bond line. We do draw formal charges. They are very important. And all other atoms that aren't carbons and hydrogens are always drawn in. So that would be the oxygens, the nitrogens, the sulfurs, other molecules, other atoms like that. For carbon chains, then, the way we normally draw them, since we're not writing the carbon symbols anymore, is we just draw the bonds themselves. And normally the chains are drawn with a zigzag kind of structure with approximate angles of 120 degrees between each of the bond lines. For rings, we normally just take the size of the ring. So if there's 6 carbons, we would draw it as a regular polygon like a hexagon. If there's 8 carbons, we might draw it as an octagon. So here are some examples. In the first case, which is 2-propanol or isopropanol, you can see the simplified bond line structure over here on the right. First of all, it has no lone pairs. There's no carbon atom symbols, and there's none of the hydrogens that are attached to the carbons drawn in, either the CH bond or the hydrogen symbols. So we just have these sort of 3 lines here. These 3 carbons are indicated by the ends of the chain and by that kink where the center one is. We do draw the CO bond. We do draw the hydrogen that's attached to the oxygen, but not the HO bond. And that's the simplified structure. You can see in the next example, we have this very large looking complex molecule, which is, it's got a lot of bonds, a lot of symbols, and it's difficult by first glance to grasp completely what's going on there. But if we simplify it and we draw the bond line structure you see on the right, it's much easier for us to see. So all the hydrogens are gone here. They're still there, they're still on the molecule. We just don't draw them in. So we would interpret that end of that line right there as being a CH3. So we assume in these bond line structures, there's enough hydrogens to make each atom have its full octet. You can see the double bond is still appearing over there. Next, we have this rather complex looking thing, a big mess of bonds and atoms. We can clean this up considerably by converting it to its bond line structure on the right. And you can see what we've done here is, again, we've dropped all the lone pairs. We've dropped all of the CHs. We're just assuming the CHs are there in the right-hand structure. We've kept, importantly, we've kept our formal charge. We need to keep the formal charges in order for us to get the structure right. So in this oxygen here on the carbon-oxygen double bond, we make the assumption that that oxygen has 2 lone pairs so that that oxygen has a full octet. Organic molecules we often think about as having hydrocarbon chains as well as other things attached to those chains. We often call those things that are attached to the carbon chains functional groups because these are things that provide function to the molecule. You can think of it like that. As well as the carbon chain itself, we often call the carbon backbone or the carbon skeleton, which we sometimes abbreviate as R. So what we're going to do in the next couple of slides is go through all of the functional groups that we will be discussing in this course. This is just a small subset. There's many other functional groups we won't talk about and you may see in future courses. However, we're going to cover the most important ones. So if an organic molecule has only carbon-carbon single bonds as well as carbon-hydrogen single bonds, we call these molecules alkanes. These are probably the simplest type of organic molecule. And here I have 2 examples. One is octane, which has a total of 8 carbons, and we can count them 1, 2, 3, 4, 5, 6, 7, 8. Octane is an important component of gasoline. And here we have butane, which is another one. This has 4 carbons, 2, 3, 4. If we were to write butane out as its full Lewis structure, we would have CH3s on the end and CH2s in the middle. If an organic compound has 1 or more carbon-carbon double bonds, we call these molecules alkenes. So alkene is a functional group that is a carbon-carbon double bond. 2 examples here are ethene and propene, which is also called propylene. And you can see the carbon-carbon double bond in these structures. Finally, if there is a carbon-carbon triple bond, we call these alkynes. Alkynes examples here are acetylene, which is used in like welding torches. And here's just another random molecule, 3-hexyne. So this molecule would be a CH3, CH2, carbon triple bonded to another carbon, CH2, CH3. So these short-handed structures, these bond line structures, are much cleaner and much easier for an experienced chemist to interpret. Moving along, we have aromatic functional groups. And aromatic functional groups often contain these 6 carbon rings, these hexagonal rings, like the one you see right here, with alternating single and double bonds going around the ring. So if it has 3 double bonds in that alternating single bond, double bond pattern in a 6 carbon ring, we call that a benzene ring or a phenyl ring. And that is the most commonly found aromatic group. So that's the group we're looking for. Just to point out as well, if you have a carbon-carbon double bond that is part of an aromatic ring, that is not an alkene. Alkene carbon-carbon double bonds are all by themselves, and they're not part of this ring type structure that has 3 alternating single double bonds. Alkyl halides are basically alkanes that have a halogen attached to it somewhere. Halogens being any element that's in group 17 in the periodic table, which includes fluorine, chlorine, bromine, or iodine, or iodine, however you'd like to say it. Alcohols are organic molecules that have an OH group attached somewhere along the hydrocarbon chain. Here we have some examples. We have 2-propanol, which we saw before, which is rubbing alcohol. This is another one, which is menthol. And you can see menthol, which is a component. I think they put it in cigarettes, but you also find it in different candies and things like that as well. Vicks VapoRub has menthol in it. You can see it has an OH that's attached to a carbon, which is attached to a big bunch of other carbons with a carbon ring. Now, I want to point out that that ring is not an aromatic ring because it doesn't have any double bonds. It has all single bonds, so it's just an ordinary hydrocarbon alkane backbone chain. Ethers are when you have an oxygen atom that has a carbon attached to both sides. So here we have a CH2 and a CH3 attached to the right side with the same thing on the other side. Thiols, coming along next, are like an alcohol but have the oxygen atom replaced by a sulfur. So thiols are well known for smelling very strongly, like rotten eggs. And you can see this example right here. Amines are compounds that have a nitrogen atom with one or more carbons attached to it. We'll see some examples in more detail later on. The next bunch of functional groups will all have a structural unit in common, which we call the carbonyl group. The carbonyl group is a carbon double bonded to oxygen, like you see here. And what distinguishes these next functional groups from each other is what else is attached to the carbon atom on the carbonyl group. If the carbonyl group has one or more hydrogen atoms, we call that an aldehyde. And so you can see the simplest aldehyde is formaldehyde, where both of the things attached to that carbon are both hydrogens. The next molecule we have here is vanillin, and vanillin is the compound responsible for the flavor and odor of vanilla. It has a carbonyl group up top with a hydrogen attached. What I want to point out here is that this molecule actually has a bunch of functional groups on it. And what we often see is single molecules having multiple different functional groups all at the same time. So in addition to that aldehyde group, you can see right here we have an aromatic ring. It's that 6-carbon ring with these alternating single and double bonds. We also have over here an ether, which is an oxygen with carbon atoms on both sides, or bonded to 2 different carbon atoms. The next one we're looking at here is cinnamaldehyde, which is, as you might have guessed, the compound responsible for the flavor and odor of cinnamon. You can see it has a carbonyl group over here with a hydrogen attached, making it an aldehyde. It also has an alkene, and it also has an aromatic ring. A ketone looks a lot like an aldehyde, except it's a carbonyl group with a carbon atom attached to both sides. Acetone is the simplest ketone. Acetone is a common name. We're going to be looking at how to name these things systematically in a little bit. And you can see acetone has that carbon-oxygen double bond. A few more examples. We have carvone, which is a flavor compound in spearmint. And here's another example, which is a complex-looking molecule. Imagine what this would look like if it was a full Lewis structure and not a bond line structure. It would look a little crazy. This is called cortisone, and cortisone is a hormone in the human body. You can see right here, for example, that I just circled is a carbon-oxygen double bond with a carbon here and a carbon here, making that a ketone. There's another ketone here and another ketone here, all shown in red. It has a few other functional groups as well. It has an alcohol here, and it has an alkene down here as well. Another good example of a molecule with multiple functional groups. Carboxylic acids are compounds that have a carbonyl group with an OH attached. And so you can see that functional group pattern right here in acetic acid, which is a component of vinegar, the primary component of vinegar, which is just acetic acid mixed with water. Aspirin as well, you can see, has a carboxylic acid as well, along with a aromatic ring. Ibuprofen, which is a common anti-inflammatory drug, has right here a carboxylic acid carbonyl group with an attached OH, as well as an aromatic ring. Esters are compounds that smell quite nice, typically. They have a carbonyl group with an oxygen attached, which is attached to another carbon. So you can see right here, you have the carbonyl group attached to an oxygen, which is itself attached to another carbon. So you can kind of think of this as almost like an ether with a carbonyl group attached. Multiple fruits, their characteristic smell and flavor is a result of esters that are naturally produced inside the plant. Banana uses this compound, 3-methylbutyl acetate, which has a carbonyl group, an oxygen, which is also attached to another carbon. You can see a number of other ones here. We have the compound responsible for the smell and flavor of apple, pear, pineapple, and orange. Amides. Amides are compounds that have a carbonyl group attached to a nitrogen, with that nitrogen having, it could be hydrogens, it could be carbon-based groups, but it's this functional pattern right here, the carbonyl plus the nitrogen, that makes it an amide. Amides are extremely common in biological compounds, especially proteins. And this molecule you see on the right is a large, complex-looking molecule called oxytocin. And oxytocin has multiple amides in this structure, which we can look for. Starting on the far left, you can see here is a carbonyl group attached to a nitrogen atom. So that makes for an amide group. Next, over here, we see another carbonyl group also attached to a nitrogen. Here is another carbonyl group attached to a nitrogen. It's another amide. Another carbonyl group attached to a nitrogen makes that another amide. We have an amide here, an amide here, an amide here. Lots of amides. One here, one here, and one here, for a total of 11 amide groups in oxytocin. Oxytocin is a hormone that is produced when you feel happy. And apparently dogs start releasing oxytocin when you start petting them, which is nice. Nitriles are functional groups that have a carbon triply bonded to a nitrogen. Okay, and so here's a few examples. We have crambine, which is an anti-cancer compound that is present in cruciferous vegetables, which is the family of vegetables that includes things like broccoli and Brussels sprouts. And it has right here, that's a carbon atom right there, triply bonded to a nitrogen. It's called a nitrile. This is another one. Sometimes for carbon-nitrogen bonds, we just abbreviate it CN, which is understood to be carbon triply bonded to a nitrogen. So here's some practice before we move off of functional groups. The first molecule on the left is an anti-cancer drug that's derived from the Pacific yew tree called Taxol. And what we're asked to do in this case is identify as many different functional groups as we can and circle them. Well, to begin with, we have aromatic rings here and here on the molecule, which we can label aromatic. Next, you can see there's a carbonyl group with a nitrogen attached, which is an amide. Over here, we have a carbonyl group with an oxygen, which is itself attached to another carbon. That is an ester. Over here we have an OH just on a regular carbon. That is an alcohol. What else do we have? We have another alcohol over here. Right here, a carbonyl group, oxygen attached to a carbon is an ester. Here we have a carbonyl group with a carbon on both sides. That is a ketone. Over here on the right, we have an oxygen atom that has carbons attached on both sides. That is an ether. Not to be confused with ester, which looks like this. Carbonyl group, carbon on the oxygen. We have another aromatic ring over here. We have another ester over here, and we have another alcohol over here. The last thing in this molecule is right here, carbon-carbon double bond, which is an alkene. So this is a very busy molecule with lots of different functional groups. The next molecule here on the right is called rapamycin, which is a drug that was isolated from a bacteria, I think, in the soil on Easter Island, which is called Rapa Nui, which is where the name rapamycin comes from. And it's a drug that's given to prevent organ transplant rejection. So this has a few different things. It has an alcohol. Over here is an ether. Moving down and to the right along the chain, that's a 6-carbon ring, by the way, but not an aromatic ring. It's not aromatic because there's no alternating single and double bonds. Moving down, you can see that there is this group here, which is a carbonyl oxygen carbon ester. Moving to the right, we have a carbonyl group with carbons on both sides, which is a ketone. Moving along, we have a carbon-carbon double bond, which is an alkene. Keep going, we have an OH, which is an alcohol. We have here an oxygen with carbons on both sides, which is an ether. Here we have a carbonyl group with carbons on both sides, which is a ketone. Moving down and around, you can see there are multiple carbon-carbon double bonds. These are all alkenes. They're alternating single-double, but they have to be in a ring to be considered an aromatic group. So these are not aromatic. These are just alkenes. Next, oxygen with 2 carbons on each side is an ether. This is also an ether, an oxygen with carbon on both sides. Here we have an OH attached to a carbon, which is an alcohol. Here we have a ketone, carbon double bond oxygen, carbon on both sides. And I guess this is our last one. We have an amide, a nitrogen attached to a carbonyl group. So again, another busy molecule. Very often organic molecules have many different functional groups. For our naming though, we're going to keep it much simpler than these molecules. We're going to be looking at molecules with 1 or possibly 2 functional groups max. So to start, we need to know the names of the base chains. The basic chains in organic chemistry. We can think of these as just carbon-carbon bonded chains with some number of carbon atoms. And these can be as long as, millions of carbon units, hypothetically. But we're going to limit ourselves to only chains that have 10 carbons or less. Or I guess that should be 10 carbons or fewer. And we have names associated with each carbon chain. So the name for the alkanes of length up to 10, if it's got 1 carbon, it's called methane. And we would call the first part of this word, the prefix, the root name for a carbon chain of 1 carbon long. 2 carbons is called ethane, 3 propane, and 4 butane. And those are names you're going to have to become very familiar with. After that, the names make a little bit more sense because the prefixes actually correspond to the number of carbons in the chain. So we have pent, pentane. Pent means 5, just like a pentagon. And so 5 carbons is pentane. 6 is hexane, just like hex is 6 for hexagon. Moving down, heptane is 7, octane is 8, nonane is 9, and decane is 10. These are names you're going to have to commit to memory, and we're not going to go longer than 10 carbon chains in this course. You can also have cyclic alkanes, and we're not going to spend much time looking at the nomenclature for cyclic alkanes, but you should know that they can exist. We typically draw them just as regular polygons with that same number of carbons. So cyclobutane, which has 4 carbons, we draw just as a square. And you can see that the name is the same as the name of the single chain, except we add the word cyclo to the front. So if it's in a ring, we put a cyclobutane, cyclopropane, cyclohexane. And if it's not in a ring, we drop the cyclo and it's just propane, butane, pentane, hexane. So to name alkanes, and this is only going to be for what we call linear alkanes. We're not going to look at the cyclic ones in this course. We're going to start by finding the longest carbon-carbon chain in the molecule. And this is what we would call the base chain. So if we look at this first molecule right here, what we would want to do is identify the longest possible carbon chain, which I have done here on the right. That longest carbon chain has 6 carbons, which a 6-carbon chain we would normally call hexane. You could find another carbon chain that's shorter. If you started down here, 1, 2, 3, 4, 5, that would not be the longest carbon chain, so that would not be the base chain. So step 1, find the base chain, find the longest carbon-carbon chain. Step 2, look for anything that's attached to that longest carbon chain. We're going to call these things substituents. Sometimes we also call them branches. So in this case, we have our base chain right here, which is circled in red, and we have one thing attached to that base chain, which is a single carbon attached on carbon 3, and that carbon, it's a CH3. Right? This is a bond line structure, so that would be a CH3 attached at that point in the chain. So this branch has 1 carbon, excuse me, this branch has 1 carbon in it, and one carbon chain is called methane. So what we do if it's a branch off of the main chain, we change its name by dropping the ANE and adding YL. So methane will lose its ANE and be changed to methyl. So a branch is just the name of the alkane ending in YL. So we call that methyl. The next thing that we have to do is figure out how we're going to number these carbon chains. So you can start from either one end or the other end of the base chain. In fact, what you should do is start at both ends and number it in both possible ways. So if we start at the left-handed way, we're going to go 1, 2, 3, 4, 5, 6 as indicated by the blue numbers. Or you could start from the right side and label it 1, 2, 3, 4, 5, 6 starting from the right side. Then what we want to do is decide which of these numbering schemes makes more sense. So what we want to do is look for any substituents, and the first substituent we come across, we want it to have the lowest possible number. So if we use the blue marking or numbering scheme here, we end up giving our methyl group, we find it at position 3, attached to carbon 3. If we use the red numbering scheme, we would end up finding that methyl attached at number 4. So the correct numbering for this molecule would be the blue numbering scheme because it gives the lower number 3 to the methyl group as opposed to the red scheme, which would give it 4. So then what we do is we take our base chain, we write down the name of the base chain, which we said was hexane. Then before this base chain name, we will list our substituents, and before each substituent, we put the number where it is attached to on the base chain. So we've decided we're going to use the blue scheme here. That means the methyl gets number 3. So we would name this molecule 3-methyl hexane. You can see that listed down here below. If there's more than one substituent, you list them all, and you list them in alphabetical order. If there's more than one substituent, we do alphabetical order separated by dashes, and we put the position number for each of the substituents. If the substituents are the same thing, if there's multiple of the same substituent, instead of saying 3-methyl, 4-methyl, 5-methyl, 5-methyl, 6-methyl, we bundle them all together, and we use prefixes di, tri, tetra, penta, etc. to show how many of that type of substituent there is. This is going to be easier to show you in an example, so we're going to take a look at the molecule you see right here. First thing we do is try to identify the longest carbon-carbon chain, which I will circle for you right here. That has 8 carbons. So our base chain for this particular compound is going to be called octane. If you look at substituents that are attached, we have a 1-carbon chain there, 1 carbon, 1 carbon, 1 carbon. Each of these would be methanes, so we drop the ANE, add YL. We have 4 methyls on this compound. When we're numbering this chain, we want to start from the right side. We go right to left, and we go 1, 2, 3, 4, 5, 6, 7, 8. So we have 4 methyls. 2 of them are on carbon 3, and 2 of them are on carbon 4. So because we have 4 methyls, we would say not methyl, 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 methyl. We would say tetramethyl to indicate that there's 4. And when we list before tetramethyl the numbers showing the positions of those 4 different methyl groups. So the name of this becomes 3, 3, 4, 4 tetramethyl octane. Here's another example. What we're going to do is find the longest carbon-carbon chain. And if we start from up here, we can find a carbon chain that goes down this way. This will be our base chain. And this has 9 carbons, so our base chain in this case is going to be nonane. You can see we have a 1-carbon substituent here, which is going to be a methyl. And over here we have a 2-carbon chain attached. And an alkane with 2 carbons is called ethane. So this one becomes ethyl. Okay. Next thing we have to do is number this chain. We could start from left to right and get 1, 2, 3, 4, 5, 6, 7, 8, 9. Or if we went from the other direction, you would get these numbers. I'm not going to even write them out. In this example, the first substituent we come across is methyl, and it comes at carbon 4. If we went in the other direction, the first substituent we would come across would be ethyl, and it would get number 5. So we want to choose the numbering system I already put down because we want the first substituent we hit to have the lowest possible number. All right, so what this becomes then is we have a 4-methyl and a 5-ethyl using this numbering scheme. We list each of the substituents out, and we want to list them out in alphabetical order. So the name becomes 5-ethyl, 4-methyl nonane. Here's one more example. We need to find the longest carbon chain. And so starting on the far left, we can find this chain as being our longest. Sometimes the longest chain is not the obvious one, so sometimes you might have to spend a little minute looking to see what they all are. Next we have a methyl, a methyl, and a methyl. There's 3 CH3s attached to this main chain, and we have to decide which way we're going to number it. It works out if you start left to right. We go 1, 2, 3, 4, 5, 6, 7. Or if we went right to left, you get 1, 2, 3, 4, 5, 6, 7. The first substituent we hit going left to right is on carbon 2. And then the first substituent you hit going right to left is also carbon 2. So in this case, what we do is we look for what's called the first point of difference. So if there's a tie starting from the left side to the right side, basically forget about those first substituents and then look to see the second substituent. So starting from left to right, the second substituent we hit is also on carbon 2 because there's 2 substituents on carbon 2. Starting right to left, the first substituent we get to is on carbon 6. So we want to use the numbering system on the bottom to give the lowest possible number to the second substituent. So 226 will be 266. We have 3 methyls, so we have trimethyl. And the positions will be 2, 2, 6, trimethyl, and our name is 226 trimethylheptane. Notice between methyl and heptane, there's no space, there's no dash. Trimethylheptane is one big long word. Next, alkyl halides. Alkyl halides are basically named the exact same way as alkanes, except the halogen substituents, which is in this case chlorine, what we do is we drop the INE and add an O. So chlorine becomes chloro, and we treat them just the same way we would treat a methyl or an ethyl or some other alkyl side chain. First thing we do, we have to identify the longest carbon chain, which looks like that. And then what we have to do is decide which direction we're going to number it from. If we start from the left, we get 1, 2, 3 for our first substituent that we come across, which is this, which is an ethyl. Starting from the right, we get 1, 2. So that chlorine is the first thing we hit starting from the right side on carbon 2. So the numbering system should start from the right so that the first encountered substituent gets the lowest number. 2, 3, 4, 5, 6. We have a chlorine on carbon 2, which we'll call chloro. And we also have a chloro over here on carbon 3. So since we have 2 of the same thing, we would call this a dichloro. And ethyl appears on carbon 4. So writing this name out, we would say there is a 2,3-dichloro, 4-ethylhexane. The reason chloro here comes before ethyl is chloro comes before it alphabetically, and these are listed in alphabetical order. I will point out that for dichloro, we use the C when we're looking at the alphabetical order here, not the D. The prefixes here don't count in the alphabetical order for the different substituents. It's chloro versus ethyl. I mean, either way, it's going to come first alphabetically, but we should be looking at the C in the name for alphabetical ordering. Okay. So for alkene nomenclature, alkenes have carbon-carbon double bonds. First thing that we need to do is we need to make sure that our base chain, which is our, what we're naming the whole compound based on, contains the carbon-carbon double bond. So we need to find the longest carbon chain that has that double bond, and we can find that pretty easily, I think, if we follow this route over here. Now in alkenes, we can have branches as well, like you see here. We have methyl, 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 which would be a trimethyl. But when we're numbering these things, what we have to do is give priority to the alkene. So the lowest number doesn't go to the first substituent we see. We have to number it from the direction that gives the lowest possible number or lower possible number to the carbon-carbon double bond. So that's going to be starting from the left here, which is 1, 2, 3, 4, 5, 6, 7. What we do for our base chain name is we take whatever the alkane name would have been for that chain, which was heptane, and we drop the ane and replace it with ene for alkenes. So this becomes a heptene. Next, we just take the substituents that are there, which are 3 methyls, which would be a trimethyl. So let's put that in. Trimethylheptene, and we have to give the positions of the 3 methyls, which are 5, 6, 6 trimethylheptene. In this example, we have an alkene where our longest carbon chain is basically all of the carbons. And in this case, the numbering scheme left to right or right to left gives the lowest number to the alkene, which is the same in both directions. You start on the left, you get 1, 2, 3, 4, or starting from the right, you get 1, 2, 3, 4. So if it doesn't matter which way you name it for giving the lower number to the alkene, then after that you would consider any substituent on there. So for this molecule, because it doesn't matter for the alkene left or right, we turn to the bromine that's attached and we want to give it the lower number if possible. So we're going to number this right to left to give it the number 3, because if we went the other way, it would get the number 5. 4, 5, 6, 7, 8. So 8 carbon chain becomes octene, and we have a 3 bromo-octene. One thing that we have to do when we're naming alkenes is actually indicate the position of the carbon-carbon double bond itself. Okay, we did this in the previous example by putting a 1 in front of the name of heptene, because carbon 1 is the first carbon where that double bond starts. It's between carbons 1 and 2. In this case as well, we want to say this is a 4-octene because carbon 4 is where that carbon-carbon double bond starts. So this molecule will be named 3-bromo-4-octene. Next, alkynes. Alkynes are named the same way as alkenes, except instead of ene, we have yne in the name. We need to find the longest carbon chain that contains the triple bond, which in this case would be going in this way. It's always good to count these to make sure you have the longest possible chain. And we have priority for the triple bond over other attached groups. So in this case, we want to give the lower number to the alkyne before we worry about this attached group, which is this 3-carbon group, which is propyl. Why is it propyl? Well, it would be propane if it's 3 carbons, but because it's a side chain, we call it propyl. So we're going to number it starting from the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this becomes a non-9. And we're going to put a 2 in front of the non-9 to indicate the position of that carbon-carbon triple bond. In front of this, separated by dashes, we're going to list the position of the side chain, which is the propyl. So we're going to have 5 propyl, 2 non-9, which you see down here. Alcohols. Alcohols contain an OH, and an OH also takes priority over other substituents on the chain, especially, well, alkyl and halogen substituents on the chain. So what we need to do is find the longest carbon chain that has the OH, and we want to number it in the direction that gives the lower number to the OH. So let's do that here. The longest carbon chain with the OH is here. And we have carbon 1 with the OH, 2, 3, 4, 5. A 5-carbon chain is a pentane. Because it's an alcohol, we drop the ane and replace the suffix with ol. Sorry, not the ane, we just drop the e. So this becomes pentanol. We have to put a number in front of the pentanol to indicate the position of the OH. So we're going to put a 1 here because the OH is attached on carbon 1. And then we have 2 methyls on carbon 4. So we would call this 4,4 dimethyl 1 pentanol. Here's another example. We find the longest carbon chain that has the OH, which is in this direction. Starting from the left, if we numbered it, we would give number 4 to the OH. But we don't want that. We want the OH to have the lowest possible number, so we start instead from the right. And we go 1, 2, 3, 4, 5, 6. So this becomes a, well, we give the OH here number 3. So the longest carbon chain has 6 carbons, which is hexane. We drop the E and put OL to make hexanol. We put the position of the OH group, which is on carbon 3 in front. And then we list out any substituents, which is an ethyl on carbon 4 to get the name 4-ethyl-3-hexanol. Thiols is basically following the same rules as for alcohols, except instead of dropping the E and adding OL, all we really do is add the word thiol to the end of the ane base chain. Thiols, the SH group gets priority over other halogen and alkyl substituents, so we number it to give the SH the lowest possible number. So we find the longest carbon chain, which is, I guess, the whole carbon chain here. And this has 8 carbons in it, which would be octane. But because this chain has an SH on it, the base chain becomes called octane thiol. We put a number in front of octane thiol to indicate the position of the SH. So we would number this chain 1, 2, 3, 4, 5, 6, 7, 8. We number it in this direction, starting from the left, because we want the SH to have the lowest possible number. This puts the bromine attached to carbon 8. So we take bromine, drop INE, and add O to make it 8-bromo-2-octane thiol. Next are amines, and amines come in different flavors. You can have primary, secondary, and tertiary amines. If the nitrogen is attached only to a single carbon atom, we call it primary. If it's attached to 2 different ones, it's secondary. If it's attached to 3 carbons, it's a tertiary amine. All right, so in this case, we're going to be looking at primary amines, and this amine that's drawn here is a primary amine with 1 carbon group. So what we do is we find the longest carbon chain that has the NH2 group, which is this. That's 4 carbons, which is butane. And what we do to name amines is we take the alkane name, drop the E, and put amine on the end. So butane becomes butanamine. All right, we number the chain to give the lowest possible number to the nitrogen. So that becomes 1, 2, 3, 4. So this becomes 2-butanamine. And then we take any substituent and list it in front, along with its number to indicate its position. So the fluorine here is on carbon 3, so our name becomes 3-fluoro-2-butanamine. So we talked before, we said we had tertiary and secondary amines as well. We're not going to bother with the nomenclature of these ones here. Maybe in some future course you can worry about those. Ethers. Ethers have an oxygen with 2 different alkyl groups. There's a few different ways that are acceptable to name ethers, but we're going to be consistent and just stick with 1. And so what we're going to do is look at ethers that have we're going to look at these as having a long chain on one side and a short chain on the other side. And what we're going to do is whichever side is the longer side, we're going to choose that as our base name. And what we're going to do is take the shorter chain along with the oxygen, and we're going to call that a substituent. So in this example, we're going to take the shorter chain, which is 2 carbons, which would be ethane. We're going to drop the E and add oxy to indicate the presence of the oxygen attached to that chain. And we're going to call that whole piece that's in the box an ethoxy group. And then we just take our base name, which is the longer chain, which is butane. And we're going to number it 1, 2, 3, 4 to give the lowest possible number to the ethoxy group. And we write the name out 1-ethoxybutane. So there's an ethoxy group attached to carbon 1 of the butane. You can have aromatic groups as well and still consider it an ether. Or you can have 1 aromatic ring and 1 alkyl group. But we're not going to worry about those right now. We're going to keep things pretty simple for this course. Here's another example of an ether, and here we have a 3-carbon chain, and we have a 5-carbon chain. So the 5-carbon chain is going to be the base name, and a 5-carbon chain is called a pentane. And the smaller chain, which is the 3 carbons, we are going to join up with the oxygen. 3 carbons is propane, and so this group here in the box is going to be called propoxy. On the main chain, we would number this 1, 2, 3, 4, 5. The propoxy group is attached on carbon 3, so this is called 3-propoxy pentane. All right, we're moving through these pretty quick. Aldehydes have a carbon-oxygen double bond, which we call a carbonyl group, and an a hydrogen attached to that carbonyl group on one side, at least one side. And for aldehydes, this carbon-oxygen group is always going to get priority for the naming. Now, by definition, that carbonyl group it's right here, always has to come at the end of a chain. It's impossible for an aldehyde to have that somewhere in the middle of the chain. It's always at an end. And because it gets priority, we always give position number 1 to the carbonyl carbon. So we find the longest carbon chain that includes the carbonyl carbon, which in that case is here. We number it 1, 2, 3. We always give the aldehyde position 1. We have a methyl here on carbon 2. And we take the base chain, which is 3 carbons, which would be propane. We drop the E and add Al to make propanal. We don't have to put a number in front of propanal, though, because we know that the carbon-oxygen double bond is at position 1. So the name of this compound is 2-methylpropanal. Ketones are when you have a carbonyl group with carbons on both sides. These can be in different positions along the chain. So we do have to indicate the position of these along the carbon chain with a number. So what we need to do for ketones is find the longest carbon chain that has the ketone group. So it's there. And we want to number it from the direction that gives the lowest number to the ketone carbonyl oxygen carbon double bond, which is 1, 2, 3, 4, 5, 6, 7. We have a substituent here, which is an ethyl on carbon 4. Priority goes to the carbonyl group when we're numbering it. So 7 carbons would be heptane. For naming ketones, we drop the E and add ONE. So heptane becomes heptanone. Carbon 4, we have an ethyl. And we have to indicate, as I said before, the position. I didn't leave myself a lot of room there, but you can see that the carbonyl carbon comes on carbon 3. So we need to squeeze a little 3 in there. And we end up with the name 4-ethyl-3-heptanone for this particular molecule. Carboxylic acids are carbonyl groups that have an OH attached. As the name suggests, these things typically can be quite acidic. These will always as well come at the end of a carbon chain. So the carbonyl carbon for a carboxylic acid always gets number 1. Finding the longest chain, we have 2, 3, 4, 5, 6. And so this is going to have our base chain of hexane. And the way we name a carboxylic acid is we drop the E and we add oic acid. So hexane becomes hexanoic acid with a space between oic and acid. For this particular one, we have substituents. We have a methyl and a methyl on carbon 2, and we have an iodo. So the name of this compound becomes 6-iodo-2,2-dimethyl hexanoic acid. No space between the dimethyl and the hexanoic. Notice that the iodo comes before the dimethyl because iodo comes before methyl alphabetically, because we don't count the di when we're alphabetizing. We're comparing M versus I. For esters, basically what we do here is we take the ane suffix of the base chain alkane and we replace it with O8. Okay, so if you look at the ester itself, it has the carbonyl group attached to the oxygen. We look at the chain first that's attached to the oxygen, and we consider this almost as if it was a substituent. So in this case, we have a 1, 2, 3, 4, 5 carbon chain. And a 5 carbon chain is pentane. And because we're thinking about it as a substituent because it's on the oxygen, we're going to call it pentyl. The other part that has the carbonyl group kind of has priority for the base chain. This has 2 carbons, 1, 2, and 2 carbons is ethane. And what we do is we drop the ane and add O8. So the ethane for the base chain becomes, I guess we just drop the E. We don't drop the ane, we just drop the E. Ethanoate. So what we do is we list the substituent first, which is pentyl, and then we have a space, and then we list the name ethanoate. The base chain is always the one that has the carbonyl group. The one that's listed first, the substituent, is always the one that's attached to the oxygen. And it doesn't matter which one's longer. Here we just go by, which one is attached to the oxygen versus which is attached to the carbonyl group. We're not going to bother naming esters that have things attached to those chains. It gets a little bit more complex, but again, we're going to try to keep this relatively simple. For amides, amides have a carbonyl group with a nitrogen attached. If the nitrogen has 2 hydrogens as well, which this example does, we call this a primary amide. Okay? Primary amide, you could have one of those hydrogens replaced with a carbon, in which case it's a secondary amide, or you could have 2 of them replaced, both hydrogens, and then it's a tertiary amide, which we'll deal with in a little bit. So what we do is we find the longest carbon chain that has that amide group. We start numbering with number 1 for the carbonyl carbon. 2, 3, 4, 5, 6. For naming these things, we drop the E at the end of the alkane name, so that would be hexane. And we drop the E and add the word amide to the end. So it becomes hexanamide. like that. We don't have to indicate the position with a number because we know it's always number 1. We start numbering there, and you can see we have a substituent, which is a fluorine, which we call a fluoro, attached to carbon 4. So this becomes 4-fluorohexanamide. That's how you would pronounce that. In this case, we have a secondary amide because one of our hydrogens on the nitrogen is replaced by a carbon group, which is in this case we know an ethyl. 2 carbons attached to that nitrogen. So our longest carbon chain that has the amide carbonyl carbon is here, which is 4. 1, 2, 3, 4. So this would be a butane, which becomes a butanamide. We have an ethyl attached, and we have to indicate the position of the ethyl, but it's not along that carbon chain somewhere, so we're not going to give it a number. Instead, it's attached to the nitrogen, so we call it an N-ethyl. That means there's an ethyl on the nitrogen of what otherwise would have been called butanamide. So N-ethyl butanamide is the name for that one. This example is a tertiary amide, so we have an N-ethyl and an N-methyl. We have the longest chain, 1, 2, 3, 4, 5. So the base chain here is pentanamide. Next, we list the 2 substituents alphabetically. First is ethyl, then comes methyl, preceded by their position, which is on the nitrogen. So it becomes N-ethyl, N-methyl pentanamide. All right. Another example here, in this case, the nitrogen again has 2 carbon substituents. In this case, they're both methyls, and we list them as a dimethyl, preceded by both positions, which is N-N dimethyl. Just as if it was on a carbon chain, we would say 3,3 dimethyl or 3,5 dimethyl. Our longest chain that has the carbonyl carbon is 1, 2, 3, 4, 5, 6, 7, 8. So this starts from octane, and it becomes octanamide. And before the octanamide, we list the 2 substituents, and we get NN dimethyl octanamide. And notice there's no space, again, between the substituents and the base chain name. So sometimes you can end up with pretty long names for these things. All right, that's it for our organic nomenclature. That is not an exhaustive list of nomenclature rules. There's lots of compounds that those names are not sufficient to name. You will not be responsible for them in this course. There's in fact a book published by the International Union for Pure and Applied Chemistry, IUPAC, which is over 100 pages long, which has names for every possible compound. One thing that we often do in chemistry, and this is something you become very familiar with when you're working in labs, is that very often the systematic names that you would get from following the IUPAC rules are very large or unwieldy or not commonly used. And instead, what we often do is refer to those same compounds by what we call common names. And here's an example of a very common molecule that you probably use every day. This is called sucrose. Sucrose also goes by the name of table sugar, and you might put this in your coffee. The IUPAC name for this name is listed here, a very long complex name, which if you pronounced it would be 2R, 3R, 4S, 5S, 6R, 2, 2S, 3S, 4R, 5R, 3,4-dihydroxy, 2,5-bis hydroxymethyl oxyl and 2-ol oxy 6-hydroxymethyl oxane 3,4,5-triol. That's a mouthful. That is not something you would want to say in place of sugar every time you wanted to talk about white sugar. So this is a good example of why common names are still useful. Sometimes it's habit, sometimes it's because it's much more convenient. On the next slide, what we have here is a list of what I would consider 10 very commonly used compounds in the lab. that go by names that are typically not the IUPAC name. So this first molecule you see over here, which is a ketone, would have the IUPAC name propanone because it's a 3-carbon chain. So that's propane, and then it's a ketone, so it's propanone. The common name for this is acetone, and anyone working in a lab will call this molecule acetone. So these are common names that it's important to be familiar with if you're working in a lab. This compound is commonly called acetic acid, even though its IUPAC name is ethanoic acid. This compound is ethyl ethanoate, following our IUPAC nomenclature that we just learned. The common name for this is ethyl acetate. Ethyl acetate and acetone, compounds 1 and 3 here, are commonly used in nail polish remover. The next one, which is a CH3 carbon-nitrogen triple bond, which would be a nitrile, would have an IUPAC name ethanonitrile, but everybody in the lab calls it acetonitrile. The next compound is a single carbon with 1 hydrogen and 3 chlorines. This would be called trichloromethane. It's IUPAC name, but the common name for this is chloroform. This next one is a ketone as well on a 4-carbon chain, so this would be called butanone. The common name for this is methylethyl ketone, which is an older name, or sometimes MEK. It's a common solvent used in lots of different applications. This is an aldehyde, a carbonyl group with a hydrogen on both sides. Common name for this is formaldehyde. IUPAC name is methanal. This compound its IUPAC name would be ethoxyethane, as we would have looked at the rules, or ethoxy-1-ethane, I guess same thing. Common name for this is either diethyl ether or just ether. The next one is dichloromethane, which is commonly called methylene chloride, a very common organic solvent. And the next one we're looking at here goes by the name 2-propanol. Common name for that is isopropanol, or also rubbing alcohol. So that wraps it up. What we've done is we've looked at the rules for naming the most common functional groups, at least simple examples, the simplest examples of those functional groups. And we also looked at what I might consider maybe top 10 most common compounds that go by names other than the IUPAC name, which are very useful to be familiar with.